So now that we've seen how to sketch graphs of polar curves, so for example, equations like r equals f of theta, we can now sketch the set of all points that satisfy that in the polar coordinate system. We want to ask questions about slopes of tangent lines. So I'm just going to quickly sketch out the example we finished off last time. So this was 2 cos 3 theta. We had these angles that sort of interesting things were happening at, all sort of pi by 6 and then so on. And the curve looked like this. It started out here and then it spiraled in and then out and then around again. So something like that. Just fix it up. So there was our graph, sort of 3-leaf flower kind of thing. And we want to ask now the question about finding tangent lines. So for example, I'm going to, in this next example here, we're going to look at trying to find the equation of that tangent line there. What's the equation of that tangent line? How do we do this? How do we find the equation of a tangent line? Do we have to sort of reinvent calculus for polar coordinates? Or maybe we can just take our polar coordinates, convert them to Cartesian coordinates, and then use all the tools we've developed throughout the course of the term to study the calculus on Cartesian coordinates. And that's what we're going to do here. So what do we do first? I want to find the derivative. So how do I find the derivative at a point on the curve? Well, I take my polar coordinates, my r and theta, and I convert them to Cartesian coordinates. So x is r cos theta, y is r sine theta. Now the key thing to note here is that r and theta are not entirely independent anymore because r is related to theta. So we're thinking of this as f of theta cos theta, and y is f of theta sine theta. So x and y change in terms of this variable theta. This is exactly a parametrization of the curve now using Cartesian coordinates. We've now got parametric equations. We've got x and y described in terms of a third parameter, theta. So now we can use the tools that we developed for finding tangent lines to parametric equations, for parametric curves. How do we do that? Well, for parametrized curves, the derivative, dy by dx, is the derivative of y with respect to the independent variable divided by the derivative of x with respect to the independent variable. What's dy d theta? Well, I look at y and I see that it's a product. So I need to use the product rule there. It's the derivative of f, that's the function r, so I haven't included f below what I've just written f as, it's just r. So the derivative of the top is the derivative of the first piece, dr d theta, times the second, sine theta, plus the first function, r, times the derivative of the second, cos theta. So from there to there is just doing a derivative. And similarly for the bottom, dx d theta. Now we just differentiate the x function. It's the derivative of the first times the second, plus the first times the derivative of the second. The derivative of cosine is negative sine. So there's our formula. Now the key here is, yeah, this formula looks kind of complicated. You don't need to memorize it though. We can just derive it. What we did was we took the polar curve, wrote it in terms of parametrized equations, and then just proceeded as usual with our techniques for finding tangent lines to parameterized curves. dy by d theta divided by dx by d theta. So here I just had to use the product rule. So let's look at an example of this. Find the equation of the tangent line to the curve r equals 2 cos 3 theta. So r equals 2 cos 3 theta. What I'm going to need to know is dr d theta, and that is 6 sine 3 theta. Derivative of cos is negative, so negative 6 sine 3 theta. I really need to know it at the particular point, 2 pi by 3. So what is that equal to? Actually, it's kind of interesting to think about what this should equal before we even do it. 2 pi by 3, we're way out here at the tip of this leaf. As my theta values increase, let's think about what's happening. Theta is increasing. My r value is getting bigger and bigger and bigger and bigger and bigger. And then my r value hits a maximum. And then it turns around. R value hits a maximum in terms of theta, then it turns around. What's the derivative of r with respect to theta at a maximum? Should be 0. So this derivative should be 0. Let's see if that's actually the case. -6 times sine 3 times 2 pi by 3. So that's sine of 2 pi. Sine of 2 pi is 0, so that is 0. So yeah, the derivative is 0. We expected that based on just a bit of analysis about what goes on with the r value. The r value is increasing, 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 hits a maximum, turns around and comes back down in terms of theta, so the rate of change in the r value should be 0 at that point. Okay. What else do we need to know? We need to know sine of 2 pi by 3 and cos of 2 pi by 3. Those will come up in our calculations. Let's just make sure we know what those are here. So 2 pi by 3, sine of 2 pi by 3, sine of that angle there is root 3 over 2. Cosine of 2 pi by 3 is -1/2. So those are just a couple of things we should keep in mind. So now let's go ahead and write out what our derivative is. dy by dx. That is, now we can refer to what's above, or we could just do the parametrized curves in our head, or you could write them out, but this is really all this is following from. So it's the derivative of r. In particular, we'll do it at the precise moment when theta is 2 pi by 3. So we're looking at dr d theta when theta is 2 pi by 3 times sine of 2 pi by 3 plus r. What's r? R at that point is 2. We could get that by just plugging 2 pi by 3 into this equation here. So r is 2 at that point times cos of 2 pi by 3 divided by dr d theta when theta is 2 pi by 3 times cos of 2 pi by 3 minus r times sine of 2 pi by 3. So there's our derivative, dy by dx. Now we just have to fill in all the details. What's dr d theta? That was 0, so a lot of this stuff goes away. That's 0. That's 0. 2's cancel off. I get a cos 2 pi by 3 over a negative sine 2 pi by 3. So a cos, that's a -1/2, divided by the negative sine, so it's a negative root 3 over 2, so it's 1 over root 3. So there's our derivative. That's the slope of that tangent line. What else do we need to find a tangent line? We need a slope, and we need a point. So what's the point? So for the point, we have a theta value, we have an r value. Now we need to know the Cartesian coordinates. X is equal to r cos theta. R is 2 cos of 2 pi by 3. Cos of 2 pi by 3 is -1/2, so this is -1. Y is r sine theta, which is 2 times sine of 2 pi by 3, which is root 3. So now we've got our point, we've got our slope. So what's our line? It's y minus the y coordinate of the point you know is equal to the slope times x minus the x coordinate of the point you know. And so this is y is equal to root 3 plus 1 over root 3 times x plus 1. And you could rewrite this in other ways if you wanted, but the point is we now have the tangent line to this curve. So we found the equation of that tangent line. Okay, so this is the process you want to go through for finding tangent lines to polar curves. First thing you want to do is take your polar curve and think about it in terms of Cartesian equations, parametrized equations. And once you've done that, then you can work out a formula for the derivative just by using the product rule in each case. And then pop in all the information that you're interested in. We can get the equation of the tangent line. Okay?